Also, I just started recording right now. Number five. Number five. Actually, let's read this first. So I noticed that some of you guys were confused yesterday. All right. In between my breakdown and all that talking, I'm pretty sure a lot of you guys were confused. So I want you guys to think of it this way. If you stretch a bowstring, you're basically giving it potential energy, right? You're stretching it, it has a lot of energy. It wants to do something, but you're not letting it. You're holding it back, right? You're holding it back. You're not letting it do what it wants to do. What happens when you let go of the bowstring?
It goes straight.
It goes straight. Okay. What does that potential energy turn into? The arrow gains kinetic energy, but where is that energy coming from? Yeah, pulling on the bow. The potential energy of the bowstring turns into the kinetic energy of the arrow. And so the arrow flies away with a lot of kinetic energy. I want you guys to apply that same exact logic. Apply the same exact logic to this. You have a stationary sphere, and you're trying to push this object. You're just trying to push this positive charge closer and closer together. But they don't want to be close at all. They were repelling each other. They want to repel each other. But the more you push this charge towards the sphere, what do you think you gain? What is it that you gain when you try and push and push this object closer and closer? Oh. Someone save me. Yeah, PE. That turns into potential energy, right? Electric potential. We're going to call it electric potential. So basically, as you push this charge closer and closer to this stationary positively charged object, you gain electric potential, right? It doesn't want to, it doesn't, you're basically forcing this charge to get closer and closer, even though it doesn't want to be. You give it a lot of potential energy. You think this bowstring wants to be stretched? No, the bow's default state is literally in the middle. So when you're pushing this charge, you're giving it electric potential. What happens if I were to take my hand away suddenly? What if I were to just let go of this charge? Oh, oh, oh man. Yes, the electric potential turns into kinetic energy of the charge, right? Here, I'll repeat what the slide says. Just like how if you were to compress a spring, its spring potential energy increases. As you apply a force to a positive test charge and bring it closer to a positively charged object, you increase the electric potential of the positive test charge. When you let go of the test charge, that electric potential turns into kinetic energy of the charge, right? The charge goes flying off with a velocity. The charge now has a kinetic energy. All that energy went into kinetic energy. Any questions, guys? Really, are there any questions about basically this analogy? Let's read your responses to number 5. Some of you guys are saying that my gravitational potential energy decreases as I lift the object. There is gravity in space. I'm just going to correct that. It really depends how far you are from the Earth, far you are from Earth or any planet or any object for that matter, because as long as you have mass, you do have gravity, no matter how small it is. You all have gravity, but I'm pretty sure your gravitational attraction is like in the 10 to the negative 19 meters per second squared. So nothing at all, essentially. Mostly, from what I'm reading, most of you are good. Most of you are good. So yeah, good. So as you bring a ball up, your gravitational potential energy increases. I didn't see anyone justify that though. I didn't see anyone explain why. So again, your gravitational potential increases because your height increases. The higher you are, the more work that gravity can do on you. And as you let go of that object, what does the energy turn into? Most of you were on point. It turns into kinetic energy. Guys, I showed you this simulation. Please tell me you guys remember the simulation. Right? As I lift this skateboarder, right? As I lift this skateboarder, you notice that my potential energy increases. Right? You see that my potential energy increases as I lift this skateboard. And then, well, what happens when I let go of this skateboarder? All that energy turns into kinetic energy, right? All this potential energy turns into kinetic energy, right? All this potential energy turns into kinetic energy as I fall. I want you to keep this analogy in mind, right? Because now what we're going to do is we're going to relate it to electric potential. Think about it, guys. Think about it. Think about it. Gravity attracts objects. this negatively charged object attracts positive charged. All right. So if you're basically lifting a ball against the gravitational attraction of Earth, you are giving it potential energy. And so I want you guys to apply that same exact logic to electric potential. If I'm going to drag a positive charge from point A to point B, right? I'm basically trying to force the positively charged object from its natural state, right? I'm trying to force it away from this from being attracted to the negative object. And so I need to exert work, right? I need to do work to get this, to drag this object away. And so when you drag this object away, right, when you pull this object away from what it wants, you give it potential energy, right? When you go from point A, right, if you were to drag this positively charged object and you basically move it to point B, you gain electric potential. Is there anyone that's confused about that, about this analogy? Please raise your hand or please message me. Right? Because basically you're pulling apart, you're basically pulling the positive charge away from where it wants to be. The positive charge wants to be near this negative charge, right? Because they attract. But what are you doing if you're pulling the object away, right? You're pulling the positive charge away from where it naturally wants to be. So you're giving it electric potential. You're giving it electrical potential energy. What happens if I were to suddenly let go of the object at point B? What happens to my electric potential? Oh, man. What happens when I let go of the charge at point B? I do all this work, right? I do all this work. I lift this object from point A to B, and then I suddenly let go at point B. What happens after? Yes, guys, I'm gonna do a very life expanded state. Let's pretend there's a negatively charged object here, right? Let's pretend this girl, this skateboarder, is positively charged. So this skateboarder right here, she's positive, right? Positive. God, Jesus Christ, my handwriting. I'm pulling this person away. I'm pulling this person away, right? I'm pulling this person away from the negative charge. She wants to be near the negative charge, but I'm pulling her away. In the process of me pulling her away, I'm doing work. I'm applying a force and she is being displaced, which means I'm doing work. I'm giving this person energy because we know that work is equal to delta ET, right? I'm giving her energy. Well, what happens when I just let go, right? When I let go, well, then this positively charged object, this positively charged human will now go back, will now start again falling back towards the negative charge, right? She's going to accelerate towards the negative charge because she's being attracted. So all that potential energy turns into kinetic. You guys have to think about it this way. I summarize it in this passage right here. Now, I didn't really repeat this slide because I don't like repeating my own words that I write. You usually find me doing that or not, I don't know, but basically everything I just said is written here. I just didn't repeat off the slide. I don't like doing that if I can. So you guys are just gonna have to think about it, right? If you don't get it right away, that's fine. You just have to think about it. Think about it. All right, your potential difference. Now, we didn't do number 3. You're right. We did not do number 3 at all. Oh no. Oh no, no, no. Oh no. So number 3. So I'm gonna introduce to you 2 vocabulary words. Actually, I'm gonna show you this actually. So if you're a charged object, right? Let's say you're a charged object, right? You're all over here and you exert an electric field. And I'm gonna pick a point, right? So at that point, my electric field, I can say that at this point, my electric field has an electric potential. Electric potential of 71.8 volts. I can say that, right? It has that potential energy as a possible potential energy. I'm sorry. And then I can pick another point, right? Let's pick another point. Let's say that the electric potential at this point is 24.8 volts, right? And so this is electric potential. So introducing to you these 2 ideas, I'm going to introduce to you another new word. What the hell is potential difference? What do you guys think potential difference is?
I think it's like the difference between like the closest circle minus the farthest circle.
Yeah, that's it. Yeah, that's it. It literally tells you in its name. So the potential difference is the difference between the electric potentials. So potential difference in this case would be this, right? You would do 71.8 minus 24.8, and you would get 71 minus 24, 51, 47. 47 volts. Are you guys okay with that explanation? So that's basically what potential difference is. So do number 3 for me, guys. So do number 3 for me. What is the potential difference between these 2 points? So basically, what's 25.3 minus 11.9? Let's move through this quick, guys. If you haven't finished 3, that's fine. Let's just move on. Let's just move on. I do want to finish this before period ends. All right. Let's just move on. So again, that's voltage, right? So we call potential difference voltage. I'm sure you guys have seen voltage in multiple areas, like for example, your electrical appliances, your batteries, anything that's electrical, you see voltage, right? You see a 12-volt wall socket, right? You 100% sure you guys have seen voltage somewhere. Anywhere that requires any electricity. So voltage, which is essentially your potential difference, is defined by the formula V is equal to W over Q. Because you need to do work, right? To move a charge somewhere, you need to do work, right? You need to apply a force over a displacement, which means, and you know that work is force times displacement. W is work done, Q is charge, V is voltage. Voltage is potential difference, guys. They're the same thing. Let's do this, guys. Knowns, come on, quick. Let's do 6, 7, 8 real quick, guys. Knowns. Let's go.
The potential difference is 100 volts.
What's my variable? Actually, no, I'm not gonna say it. It's V. Don't worry about it. Okay, what else do we know? W is question mark. You're trying to find out what your W is. Q, how do you know? Actually, I already spoiled it. You know your charge is 1.6 times 10 to the negative 19 because it's a proton. You're moving a proton. So W, I'm sorry, wrong formula. V is equal to W over Q. V is 100. W is W. Q is 1.6 times 10 to the negative 19. Multiply by that number on both sides. Cross that out. 100 times that. And that's your answer. I give you guys like 1 minute to copy this down. And I'm going to show you what this means, by the way. I'm going to show you how to visualize this problem. Why negative 17? Because you're multiplying it by 100. 100 is basically 1 times 10 to the 2. Are you asking me why I'm not doing like 1.6 times 100 is 160. And then you do 160 times 10 to the negative 19. So it's just because you're multiplying it by 100. If you plug it into a calculator, you'll get 10 to the negative 17. Also 100, you could do it this way. 100 is 1 times 10 to the 2. So you're adding 2 to your exponent. So I get negative 17. That's what you can also do. Alternatively, you can also plug it into a calculator. All right, guys, I want to move on. I'm going to show you what this looks like on the simulation. So basically the question is, what is the total amount of work required to move a proton through a potential difference of 100 volts? All right, so basically you don't know what exactly the electric potentials are, but you know what the difference is. The difference between these 2 points is 100, right? Because you know that 127 minus 27 is 100. So what is the work that is required to move this proton all the way over here, right? What is the work required? That's what the question is saying. That's how you want to visualize these type of problems, right? There's a charge right here. There's a charged object, and you are moving another object through its electric field. How much work do you need to do that? Well, you just use the formula. All right. That's why pretty much every formula says potential difference. You never really specifically deal with specific electric potentials. Guys, do number 7 for me. We're only going to do number 7. We're not going to do number 8. I think it's fine. So you have 4 coulombs of charge. You have 48 joules of electric energy, right? Because energy is work, right? This is essentially work. Work is energy, right? Work is equal to change in total energy. So what is your potential difference? Which is voltage. So you're going to do V is equal to W over Q. So W is 48, Q is 4, and you get 12 volts. It doesn't seem that hard, right, guys? I don't think so. The math isn't, at least. Any questions? Any questions about the formula?
So once you see what's the potential difference, this is the formula you have to use to solve for it.
Yes.
Okay.
No worries. Yes, you can hand it to me later. No worries. Guys, the next question 8 is really the same exact thing, but I'm not gonna require you guys to do question number 8. You can if you want to. It's good practice, but not really required. But you know, guys, there is homework to do. All right, make sure you do it. I hope you guys have a great weekend. All right, I'll see you guys tomorrow. See you guys on
Bye.
Monday.
Hope you have a good week.
See you guys Monday. Bye, guys.